Alright, in this video we're going to talk about Unit 7, Objective 1, which is related rates. There is a 6-step process that we want to do whenever we see a related rates problem, and it's currently on the screen. I'll read through it quickly, but you might want to pause the video to make sure you have time to write this down. But step 1, we're going to list everything that we know and that we want. Step 2, we're going to develop a model. Most of the time that's going to be a picture with what you know, and something we need to be careful about is we don't want to put numbers on the pictures that are changing, and I'll explain what I mean when we look at an example here in a minute. Then we want to take our picture and develop an equation that's going to be using what we know or want. Step 4 is the biggie. We want to differentiate both sides implicitly with respect to time t. That's going to be one of the big giveaways that we're dealing with we're dealing with related rates, is everything is going to be in terms of time t. The other giveaway is there are going to be multiple rates that are related, hence related rates. 5, we're going to substitute everything we know in after we take our derivative, and then we're going to solve for what we wanted. So I'm going to go ahead and move on to the example, so you might want to pause the video, make sure you have all that stuff written down. Alright, so here is our question. A hot air balloon is rising straight up from a level field tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So as we're reading through this, there's a couple of things that we can be pointing out. The first is we have a rate right here, right? Radians per minute is a rate, and it's asking for a rate. How fast is the balloon rising? So something like feet per minute. And we know it's going to be feet per minute because we have radians per minute and 500 feet in our problem. So we have two rates that are going to be related. So we know it's related rates. Everything's going to be in terms of time. We have radians per minute. So first we want to list everything that we know. So we know we're trying to find something about the height. So we can say h is the height. We know something's with an angle, so we'll just call the angle theta. We know that the distance from the liftoff point of the balloon to the rangefinder is 500, so I'll call that d equals 500. We know theta is pi over 4. And we know that the rate that theta is changing with respect to time, so we can say d theta dt equals 0.14, and it wants us to find how fast the balloon is rising, so the rate of change of height, so dh dt is what we want. So we know the height is h, we know the angle is theta, we know the distance is 500, theta is pi over 4, d theta dt is 0.14, and we want to know dh dt. So let's kind of put together a picture. So we have a little rangefinder over here that is 500 feet from the liftoff point of a balloon. And the balloon's kind of up here in the air. We know that's going to be h, and we know that's going to be theta. Now notice how I did not put pi over 4 in for theta. I kept it as theta. The reason for that, if you look back at your steps on step 2, I said don't put anything in that's changing. We know that theta is not always pi over 4. It's only pi over 4 at a certain instant. We know that theta is changing because we have its rate of change at 0.14. So anything that you have a rate of change for, that number does not go on your picture. Notice how we don't have any rate of change for the distance between the liftoff point and the rangefinder. Since there's no dd dt, that 500 is a constant, so that's going to stay. It's going to be on my picture. So we have the picture now. We got to think about an equation that's going to relate everything together. So we need something that's going to relate theta h and 500, and that relationship is going to be that tangent of theta is going to be equal to h over 500. Now, if we kind of look into the future a little bit, we know we're going to try to find what dh dt is, so it might be a good idea to get h by itself. So let's multiply both sides by 500. So 500 times tangent of theta is going to be equal to h. So there is our relationship. It deals with everything that we've talked about. So the next step is to differentiate both sides implicitly with respect to time t. So the derivative of 500 tangent theta is going to be 500 secant squared theta. Then we have to say d theta dt, because we took the derivative of theta with respect to time t. So this is like when we had our xy equals 4, we have to say dy dx on those problems. It's the same thing here. Every time we take the derivative of something, we have to say we took its derivative. So the derivative of h is simply going to be dh dt. Now, if you've done this correctly, everything should be able to be plugged in now. So now we know that theta is pi over 4, and we know that d theta dt is 0.14. So 500 secant squared of pi over 4 times 0.14 equals dh dt. Now, we don't have anything to plug in for dh dt, but that's okay because that's what we're trying to solve for. So if we think about secant of pi over 4, secant of pi over 4 is going to be 2 over radical 2, because cosine of pi over 4 is radical 2 over 2. So we get 2 over radical 2 squared times 0.14 equals dh dt. So 2 over radical 2 squared is going to be 4 over 2. 4 over 2 is 2. 2 times 500 is 1,000. 1,000 times 0.14 is 140. So dh dt equals 140. Now we're going to need our units. So we will say, thinking about everything we have going on here, the height is going to be measured in feet. And we know that because up in the problem we have 500 feet given to us. We also have our per minute given to us here. So our units for dh dt are going to be feet per minute. So that's going to do it for this video. We'll see you in the next one.